Hi guys, can you hear me? Can you hear me out in the back? Right, great. All right, hi. So today we're going to continue looking at graphs. That's what we started last time, okay? And primarily last time we looked at a family of algorithms that falls under the umbrella of depth-first search, okay? We first wrote sort of an algorithm that marks vertices, does nothing useful. Then we upgraded it to an algorithm that finds the connected components of an undirected graph by sort of bookkeeping of which connected component it was in. We had this explore procedure that in an undirected graph, it would start from a vertex and mark every vertex connected to it, okay? And then we went back and changed the algorithm again and added these pre and post numbers, okay? And then saw that for undirected graphs, we could infer from the pre and post numbers the connected components of the undirected graph, okay? And then we ended last lecture by saying, okay, let's move to the directed case. And before we do anything useful, let's at least see what DFS unchanged does on a directed graph, right? So we had this big example that we drew out with 3 edges, forward edges, cross edges, and back edges, okay? And all of these corresponded to how the pre and post number intervals kind of lay out relative to one another, okay? So the reason for doing that is because today we're going to apply the knowledge, or at least sort of understanding of how DFS behaves on directed graphs in order to solve connectivity problem there, okay? So today that's what we want to do. If we get to it, we'll also discuss another problem, but primarily we want to get to directed connectivity. In order to talk about it, even define what it is that we want to do, we have to take a small detour into so-called directed acyclic graphs, okay, or DAGs. So let's put connectivity aside for a moment. We'll talk for a moment about DAGs, okay? First, let me say kind of what they are, okay? So definition, a directed acyclic graph is, well, actually the name is pretty descriptive, right? So it is a directed graph, okay, that is acyclic. What does acyclic mean? There's no loops, okay? So there's no way to go off on a sort of non-trivial loop for starting from a vertex, I don't know, V1, V2, V3, V3. At some point, you come back to V1, okay? So is a directed graph. Well, sometimes you may see the abbreviation digraph, which means directed graph with no cycles. Today, directed acyclic graphs will mostly play a role as an auxiliary notion to define the notion of directed connectivity. But they are by themselves rather important and distinguished class of graphs, even for modeling, right? So if you're trying to model hierarchies or temporal dependencies, typically you will not have cycles, okay? So these are useful as modeling tools on their own, okay? All right, the first question that we want to ask is, how can we detect that a given graph is acyclic, okay? So given a digraph G, does G have cycles? Okay? So that's the first question. Just, we look at a graph. Can we even figure out in a reasonable amount of time whether it has cycles or not? Of course, you could go and look for every possible cycle, but that's going to take a very long time. So we want to do something a bit smarter, okay? So I'm going to write down, actually, maybe some of you have maybe spent time either in discussion section or in homeworks playing with pre and post numbers. Does anybody have a guess of how we can use pre and post numbers to detect whether a graph has cycles or not? there was one type of edge that we discussed last time that seems to suggest cycles. What is that edge? A back edge, right? If you remember, a back edge was an edge that went from the vertex to an ancestor, right? But if you are at that point, you came from the ancestor somewhere, right? Somehow, like you made your way down, and now you have an edge going back to the ancestor. Well, it looks like a cycle, right? So a kind of proposed algorithm would be as follows. So we have this routine is, I don't know, a cyclic. We pass in G, okay? And the way that this routine would go, it says run DFS on G, okay? And output a, I don't know, DAG, like the string DAG, if DFS reveals no back edges. Okay? So this is like, fairly informal. I don't want to try to make it much more formal, but there's two things we want to do. One is comment on the running time, okay? And then I want to go through the motions of actually proving that this algorithm is indeed correct, okay? Because we have this intuition of a back edge pointing to a cycle, but we need to prove it, yeah? So I didn't understand the question. Is the question what is a back edge, or? So we have a definition. Sorry, again, I didn't understand the question. I'm sorry. So we have a definition of a back edge, okay? A back edge is an edge u comma v, okay? Where we have the corresponding intervals of pre and post numbers, they're in a certain relation. And specifically, we wanted the fact that, need to get it the right direction. So let's write it together here. uv, first and foremost, is an edge, okay? And my u and v look the same, so u and v is back edge if, so now we have these two intervals that, and we need to figure out which one is u and which one is v. So this would be probably a tree edge if we would put, so I'm going to put v here and u here, okay? And let's reason through it. Why is it the case? Because I'm currently at u. Now I'm currently at v, and I'm not done, so okay, it's probably the other way around, sorry. I'm currently at v, and, okay, I'm going to try to, just a second, to not confuse you, because this confuses the hell out of me every time. There's maybe one thing you want to put on your cheat sheet, so you have to recompute it every time. VU, there we go. Why are they in this order? Because, so you went down somewhere here, right? And now you're currently at U, right? You're currently considering the edge UV. Now this is an edge that goes back to V, which is an ancestor, right? Now V is already on the stack, right? Here it is, it's on the stack, right? And remember that you can only pop V whenever you're done exploring everything connected to V. But guess what? U is connected to V, right? So it means that we will be done with U before we're done with V, right? So this is a back edge, okay? Now, and again, I didn't quite understand the earlier question, but if it was about what is a back edge, this is the definition, okay? And now we have a very concrete task, which is I claim that the presence of cycles is equivalent to there not being any back edges, okay? And we're going to prove this. Okay, one direction is easier, the other direction is less easy. Both of them are, neither of them is too difficult, but it's just clearer to prove it. Before we get there, though, I want to talk about the running time, okay? So we checked last time that DFS ran in time that was? yes, n plus m, right, or like v plus e. Okay, so that's kind of linear in the description of the graph. But here, it's not just we just want to write out the pre and post numbers for every vertex. We also want to make sure there's no back edges, right? So you can think about it in a couple of ways. One is that you literally first write out all these intervals, okay? And then you come back and you consider for every edge whether it is a back edge. Does it look like this or not, okay? And that's a constant time operation because once you have the edge in your hand and you're considering it, you look up into the arrays how these numbers kind of compare to one another, right? Or you could even try to think about it, you do it on the fly. As you're traveling, you're kind of filling in the pre and post numbers, right? And if you're currently looking at this edge, even though you haven't popped U and you haven't popped V, the mere fact that this is the case already tells you this is a back edge, right? All right. This is to say that the running time of is acyclic is also n plus m, okay? All right, I'm not going to try to write it. Just convince yourself that's the case. That's the question. The pre and post numbers, those are the quantities that we assign to every vertex, the interval of time that they stay on the stack that we did last time at the end of lecture. Okay? So we took DFS, we added these two lines that mark the time when a vertex goes on the stack and when it goes off the stack. Okay? When it goes on, that's the pre number, and when it goes off, it's the post number. Okay? Yeah.
So what properties do the pre and post numbers have to have for an edge to be a back edge?
The question is, what properties do you need to have? Well, if UV is an edge in the graph, certainly things that are not edges in the graph do not even have a chance of being back edges, right? And if you look at their pre and post numbers and you paint them as an interval, then they are so included. The U is inside and V is outside, okay? No vertex will be left behind, okay? So the question is, will it be a case that some vertices don't have a post number? No, they will all have a post number because the algorithm stops whenever it's done, with all the recursion calls, right? And whenever you're done with all the recursion calls, everything has been popped on the stack. Another question. Yeah. I will. The answer is no. Okay, otherwise they may be part of a cycle, but the point is somewhere in a cycle there will also be a back edge. Okay, so it's okay for a cross edge to be part of a cycle, but you will detect it through a back edge. Okay, which must be somewhere else. Okay, all right. And in particular, now we're going to prove that looking at back edges suffices. Okay, so claim. So G is kind of DAG, if and only if kind of DFS on G reveals no back edges. Okay? All right, so the proof, so there is one easier side. This is that if you have a back edge, then you do have a cycle. Well, why? Because, so you made your way from the root down to some vertex U, okay? So this is where you started. Let's call it S for start. And you're under, some particular invocation of explore. You're making your way down. At some point, you consider the vertex UV, and it ends up being a back edge. Why is it a back edge? Because you are starting to explore U, okay? You're finding another vertex, let's call it V, that has already been marked, okay? It's already on the stack, but hasn't been popped, okay? So it means that the collection of these edges together with the back edge will form a cycle. Okay, so here we haven't really said anything. This is kind of the easier side. The less easy side is that if you do have a cycle, then you have a back edge. Okay? So there's something slightly non-trivial about this because, let me write it maybe a bit bigger. Because maybe the cycle won't be so cute. Like here, because we had a back edge, we had the option of exhibiting this very nice cycle, okay, in the tree as it was sort of implied by the DFS explorations, right? But maybe the cycle, that there is some cycle, you don't know how it looks like. Maybe when DFS explores, the members of this cycle, okay, will be kind of scattered across the tree in different places, okay? So then you need kind of to say something, okay? So here's one way you can get a handle on it. So let V1 through Vt be a cycle, okay? So V1 goes to V2, to V3, and so on and so forth, up to Vt, and V2 goes back to V1, okay? That's a cycle. And say, let Vi be the first visited vertex. So you run DFS, it does its thing on a graph that you don't understand. I mean, who knows how it looks like. But certainly, because DFS will mark every vertex, in particular, it will go and visit one of the vertices in this cycle first. There must be one, right? Because at some point it visits all vertices, so it must visit one of these first. Call that first one Vi. So how will it look like? You will start somewhere, and your tree at some point will hit Vi. Again, Vi is the first one, okay? But remember, explore says that whenever you're going to run explore on Vi, everything reachable from Vi will be explored in that subroutine call. So kind of this will continue, and it doesn't mean that you will find immediately Vi plus 1 and then Vi plus 2. There will be somewhere, right? So there will be like some subtree of things here, maybe with some cross edges, God knows what, forward edges. But somewhere here, all the other vertices will be found. In particular, somewhere down here, there will be Vi minus 1. Okay? The vertex that immediately precedes Vi in the cycle. Okay, if Vi is V1, then it will be Vt, right? Now, whenever, and we know that this will happen, explore will be run on Vi minus 1. Among the various edges that will be considered, there will be the edge that goes from Vi minus 1 to Vi. But Vi is already on the stack, so this will be a back edge. Okay? So that's the proof. Okay, the slight non-triviality here is that here, like we could just take the cycle, we can see it, right? Here, the cycle could be just scattered in various ways. We just need some way to get a handle on a particular back edge. Okay? Again, the only idea here was to say, okay, name the cycle and consider the first one that is visited. Okay? So hopefully this one convinces you of the correctness of this algorithm. Okay? So we can detect. There's a question. Yeah. Yes, sorry, I will write bigger. Yeah, thank you for reminding me. Okay, so another sort of a useful algorithm that comes up a lot as a useful subroutine is something called topological sort. Okay? So this is the problem where, given G, there is a DAG. So you give me a directed acyclic graph. You want to order, remember to write bigger, order the vertices in such a way that every edge points forward. So pictorially, it's like if you write down all of the vertices of the DAG, and then you add on top of it the edges, all edges. And you want all of these to be pointing forward, okay? All right? Is the problem clear? So, can anybody suggest an algorithm that does this, given what we have said so far about DAGs? Yes. The suggestion was to start from a vertex and do a DFS backward. This is actually pretty good intuition, and actually we'll be using it shortly to understand connectivity of arbitrary directed graphs. But there's actually something more immediate that we can do with the given pre and post orders as they are. But this idea will take you somewhere. There's a question. Yeah. The idea is to take the post orders in descending order, okay? We start from the highest one, okay? Why? So is there a question or suggestion? Yeah. Why would that be? Look, for example here, if we have an edge UV, because we are in a directed acyclic graph, we don't really expect to also have the edge VU, right? That would be a cycle. But notice that the post number of V is higher. Whenever we had an explore call on U, it explored a bunch of other things, and whenever we are done, whatever comes later will be potentially some other component, right? It will have its own bigger post numbers, right? So when we're ordering different components, it doesn't really matter in which order they come from, but within each component, kind of the first vertex we start from will be the last one to be popped from the stack, okay? So it's kind of safest to make it first, okay? So let me first write the algorithm. So you're going to run DFS on G and output vertices in descending post numbers. Okay? Now, I'm not going to maybe dwell too much on this one because we have to kind of continue on these things. But the correctness of this algorithm is the fact that if UV is an edge in the graph, then the post of U will be greater than the post of V. Okay? Again, the intuition for this, and maybe that's really the proof, is that V will not be popped off from the stack until we're done with U. Okay? So if we output post numbers in descending order, we will never like violate the direction of the edges. Okay? So the correctness is because of this. Right. I really highly advise you to kind of make sure that you're comfortable with all of these sort of observations, because a lot of problems on graphs can be solved by just kind of programming pre and post numbers. Yeah. There's a counterexample to that. The question is, can we use increasing pre-numbers? So I prepared the counterexample here. It's a cute, tiny directed acyclic graph. Okay. So that's a directed acyclic graph. Let's run DFS on it. Okay. So A goes on the stack. Then we look at B. B is lonely, so we immediately pop it off. We go back to A. Then we explore C. So we are time 4. We consider this edge. It will be a cross edge. Okay? Pop it off, and at 6. Okay? So let's first see that if we output vertices in descending post number, then we do get the right answer. So A has the highest post number, so we write A. Then we write C, and then B, right? Because it's 6, 5, 3. Okay? Now we add the edges. We have A points to C and B, and also C also points to B. So everything is pointing rightward. So this is kind of the good way. Now the bad way, if we were to be outputting vertices in increasing pre-number, we'll again put first A, but then we would be putting B, okay? And then C. In this case, you will see that it is not a topological sort because there's an edge pointing back. Okay? Okay, good question. Actually, I had the counterexample. I was going to skip it, but it's good you asked. Okay. All right, where do I continue now? Here. Oh, this was our detour into directed acyclic graphs. This was just to get some intuition on how they work. Please be familiar with back edges, detecting them, and sort of sorting vertices topologically, okay? All right. So now we come back to connectivity, and we want to ask the problem of connectivity for directed graphs, okay? Now, when we consider this problem for undirected graphs, we had a rather simple definition. It said, well, look, U and V are connected if there is a path from U to V, and I don't have to worry about whether there is a path from V to U because I can just reverse all the edges, right? But in a directed graph, the fact that I can go from U to V does not mean that I can also go from V to U, right? For example, over here, I can go from A to B, but I cannot actually go from B to anywhere, right? So we're going to change our definition of connectedness and say that two vertices, U and V, are connected if explicitly we're going to require two conditions. There is a path from U to V, and there is a path from V to U. Maybe there is a different path, or maybe there is no path, right? Maybe there is just only from U to V or only from V to U, in which case we do not say that they are connected. Now, typically, to be precise, we really mean strongly connected, meaning that people will also say U and V are connected in this direction, but not the other direction. When we say strongly connected, we really mean like both directions, okay? Now, by strengthening the definition this way, we, again, have an equivalence relation. So, again, we could take any graph and partition it according to this relation, like before, all right? And the components, while before we called them connected components, now we may call them strongly connected components, okay? Okay? So this equivalence relation partitions the vertex set into strongly connected components. Now, our task now is to find these, okay? We're just asking the analogous question as last time. In order to find them, we will exploit a very sort of beautiful structure between strongly connected components that has to do with DAGs, okay? So here's a kind of claim that every digraph G is a DAG on strongly connected components. So let's parse what this means. It means that if we take the strongly connected components of a directed graph and we shrink them down to like kind of meta vertices, what we're left with is a DAG. Okay, I'm going to just go through an example right now. Let me write it here. So let's look at some, like, I don't know, messy looking directed graph to see kind of what I mean. So we have this is indeed a messy looking one. Okay, I think I put in everything I have here. All right, so this is the directed graph. Let's see. Let's see if we can at least first find the strongly connected components. So what is the strongly connected component that A is in? A is by itself, right? So kind of you can go certainly from A to A, but A can only go from B, but there's no way to get back to A. So kind of A is kind of by itself. Okay, so that's one strongly connected component. D, kind of it's also by itself, right? You can get to it, but that's it. You cannot get out. What about this region? Can anybody suggest a strongly connected component over here? Yeah, B and E are definitely in the same one. Are they? That's it? Yeah, I would say so, right? Because you can exit from B, you cannot come back. You cannot come back from E, you cannot come back to E, right? So B and E are definitely by themselves, okay? C and F kind of is a similar reasoning, right? You can get into C and to F, but once you leave the only way from here, there's not a way to come back, okay? So that's another component. What about this mess down here? So this is like, you know, mini cycles. You can kind of shrink it, right? But then there's this bigger cycle too. And you can shrink that too, right? So this entire thing is. So these are the strongly connected components. If you shrink these down and you look at the graph underneath, let's write it like this. So this is the graph that you would get, okay? And notice that this is actually a DAG, okay? Let's try to understand why is it a DAG. If there were a cycle between any number of strongly connected components, what would happen? It would, again, shrink back to like a super strongly connected component, okay? So our problem was to find strongly connected components. Now we know that strongly connected components are connected via DAG, okay? And this structure that is kind of superimposed upon them will actually help us design an algorithm to find strongly connected components. Okay, that's why we started talking about DAGs today. Okay? Everybody comfortable with the lines we drawn here and how we shrunk it down here? Okay. All right, so now let's design an algorithm that will help us basically find these sets. Okay? So let's do it up here. Well, let's think of some intuition. So we don't really have much at our disposal. We basically have only DFS, right? So we're going to have to somehow recycle something about DFS to help us, you know, this notion of exploring. So let's see. if I were to run explore from A, where would I go? Kind of everywhere, right? That doesn't seem like a very useful place to start. If I were to start from D, where would I go? Nowhere, right? That's actually a good thing, right? Because that kind of is what I wanted to establish. Okay. If I were to start from H, where would I go? I would go around this, and that's actually pretty interesting, right? Because I'm exactly traveling where I wanted to go, right? I'm not exiting, right? And that's kind of the point, right? So if you start, but that's not true everywhere, right? So let's say that if I started here, I will spill into here and read all of this, right? So this intuition tells me that if somehow I'm able to run explore on a sync SCC, SCC stands for strongly connected component, and if I start from a sync one, then I can find it all and then remove it, right? Here's an idea. I could say, let's say that somehow I have a way of finding some node in a sync strongly connected component. I could say, well, I found it by magic. We don't know yet how. I explore. I can remove this, and I recurse. Maybe I'm going to start from here again. And I explore this, and I remove it. Then maybe I start from here, I remove it. Start from here, remove it, and then I'm back to here. Okay? So the idea is to recursively find some vertex in a sync SCC, so you don't spill into other SCCs, and you just explore that one. Okay? So that's the idea. However, how are we going to find how are we going to constantly find a sync SCC? That's kind of not clear. However, what is clear is how to find a source SCC. Okay, so we're going to first talk about that. Okay? And the idea is that if we find a source SCC, it's enough for us. Why? Yeah? Excuse me? No, I do end up at a sync, but I don't. So the question was, why is it fine that I start at a source SCC? The suggestion was, well, I will end up at a sync SCC. That's actually not quite true, right? Because if you start, say here, you explore everything, but you don't know when you are in a sync SCC. You just kind of end up marking everything. The algorithm doesn't know, right? Yeah? Yeah, I can reverse all the directions, okay? So if I were to take this graph and flip everything, actually this would also become a source SCC. Okay, so if I can find a source SCC, that's enough for me because I start with the graph that I have. What I wanted was a sync SCC. I just flip all the edges, find a source SCC of the flipped graph. Okay, and that's kind of good enough for me. Okay, so let's first talk about how we find the source SCC. Okay, so let's say call it as a side question. So, given a digraph G, find any V in a source SCC. Any ideas of how we might do it with pre and post numbers? So a vertex in a source SCC will presumably be, more to the left here, right? So what's a good idea?
Will it have the biggest any vertex in the SCC have the first vertex in a source that we visit will have the biggest post number?
Yeah, it's a good suggestion. So it says certainly the vertex with the biggest post number should be in a source SCC. Okay? Because that's the guy that was popped last, right? So he's not like underneath anybody else. Okay, so that must be in a source SCC. And in fact, more generally, okay, so the answer is that any vertex, so the vertex with largest post number, okay? That's really the answer. So now we are ready to kind of write an algorithm for strongly connected components. I want to write it in a board by itself. So let's call it SCC of G. So the first thing we're going to do is we're going to deduce, let's call it G reverse from G. This is an operation, right? Because G is given to you as input. You want G that has all the flipped vertices, you have to do something, right? So for instance, if you have the adjacency list, you have to kind of do an operation that kind of reverts kind of all the edges, right? Or if you have an adjacency matrix, then you can just like flip it, okay? So this is an operation that costs something. You can do it in linear time. Then we can gonna run DFS on G to the R to have the post numbers. Okay, so by running DFS, now kind of it spits out all of these numbers, and you actually kind of already spit them out in order. Okay, and now what we can do is we can say for each V in V in reverse post order of G to the R. Okay, so we are considering them from the highest post number to the lowest, but in G to the R. If we have not visited V, then we're going to explore V, okay? And then, once we're done exploring it, remember that here we're thinking as if we are somewhere in a sink here, right? Notice that explore is on G, not G to the R. Okay? And then after I'm done exploring, I'm going to increase the counter, the global counter of which strongly connected component I'm in. Okay? So what's happening? Let's think about this, okay? So the idea of removing vertices from the graph is just the fact that I'm visiting vertices, right? So if I'm just visiting all of these guys, then the next time I'm calling explore, it will just ignore any edges that go to things that have already been visited. So we're kind of removing chunks of the graph that we're done with by virtue of just exploring them. Except that we're just exploring them in a very particular order. We first explore here, and then we are proceeding to the next vertex in descending post numbers. Okay? So it will either be this one, or that one, right? Whichever comes first, it will get visited, right? Things will be marked, and so the next time it will be some vertex inside this piece here. Okay? Maybe this one, okay? Actually, after you cancel this one, this is the only sink, so it will be this one, then that one, then that one. Okay? Now, of course, when I write explore GV, I didn't open it up. Inside explore GV, we will be assigning some label to V that says the current SCC number, assign it to V, right? But we're going to increase it only when we're done exploring everything reachable from V, which, if we are in a sync SCC, it is the SCC itself. Okay? So you can think this is like a very fragile algorithm, right? The order matters a whole lot. It's basically DFS. It's literally DFS in a very, very special order. Okay? Okay. So are there questions about this? Yep.
So in the second step, does it matter where we start on the graph?
So the question in the second step?
Yeah, so when we run DFS on G readers, does it matter where we start DFS?
No.
So that will affect the order of the post numbers, right?
It will affect the orders of post numbers, yes. But it doesn't matter. Because the highest post number will be in some source SCC of GR, which is some sync SCC of G. Yeah, I mean, look. Here, there are, this is a sync SCC, that's a sync SCC, right? We could start from either of these, right? That's two answers. We're kind of running DFS twice, right? Once here, right? And the other time, this is basically DFS. Okay? This is a really cute and elegant algorithm, okay? And I encourage you to look at it offline a little bit longer, because now we're going to move on, okay? But this idea of reversing vertices or just like messing with the graph in controlled ways, this is something that you should try to kind of feel comfortable with, right? It's because graphs are so combinatorial and so kind of unstructured, there's only so many operations you can try to think about when you try to kind of be creative about coming up with algorithms, right? Flipping edges should definitely be somewhere in your toolkit. You know, you can also try to sort of augment the graph in various ways. We'll see some examples like that later in the course, but you know, flipping edges should not be a weird operation in your head, right? You should be kind of feel comfortable with it. Okay, so that's it in terms of connectivity. We're now going to start a sort of kind of smaller subunit within graphs that has to do with paths. Okay. So far, we were just concerned with kind of understanding the structure of the graph. But for instance, DFS doesn't understand if a vertex is far or not from where you start in Explore, right? So now we're going to start discussing shortest paths. Okay? So let me try to give an example and define what is our next sort of set of goals. Start from here. So it's a new topic. Shortest paths. Okay, so let's define it kind of by example. Let's say that we're going to start first with undirected graphs. Right, so here's a small undirected graph, okay? And for the next sort of, I think, 1.5 to 2 lectures, we'll always have a starting vertex, okay? So we'll denote it maybe with like, you know, double circle to denote that is kind of our home base. And from there, we want to measure distances, not just to one vertex, but to all other vertices, okay? So right now, when we don't label the edges, we're for now assuming that we have unit distances, okay? So we're thinking of all the edges as kind of equally weighted in terms of cost. So just to make sure we understand, what are the distances from A to A, B, C, D, E? So what's the distance from A to A? 0, okay. To B? To C? 2, right? To D? E? All right, cool. All right. So we want to be able to fill in such a table for an arbitrary graph that is given to us, okay? Undirected graph. So what I find is find all, distance of A to all other vertices. Okay? So it's not just can you get there, but what is the shortest number of steps you take to get there. So anybody have any idea of how we might go about doing this in a kind of a generic graph? Yeah, so BFS, so-called breadth first search, is the algorithm that does that. And so let me try to kind of, without jumping first into the algorithm, give some intuition of kind of one way that at least I think is useful to think about. So you have some arbitrary graph. You have your starting point here. Let's just kind of imagine it's in the center, like kind of conceptually. And this vertex is the unique vertex that has distance 0 to itself. I mean, to A, right? A is the only thing that has distance 0 to A. Now, what are the vertices that have distance 1 to A? Who are they? They're their neighbors, right? So kind of whatever has, is directly connected to A, that is kind of all vertices that have distance 1, okay? Now, what are the vertices that have distance 2 from A? They're the neighbors of the neighbors, but for the ones that we have already seen, right? Because, this one over here, yes, he has a neighbor that, is off out somewhere, but, A itself is also a neighbor, but we're going to discount that, okay? We're going to say they're whatever neighbors of the neighbors we have not seen already, okay? So, kind of the idea is you want to first look at everybody of distance 0, then everybody at distance 1, then everybody at distance 2. And the way you're going to make progress is that at the frontier, you're going to be asking, okay, let's go around the current frontier and ask each of these vertices to give us its neighbors. I will discard the things I've seen already, and the things that are new, I'll call them to have distance whatever it was, plus 1. Okay? I go around the circle, at some point I'm done, and have a new bigger circle. Right? This is the idea of breadth first search. I'm just going to write kind of the algorithm for it. Okay? But it's rather natural. Right? There's nothing like kind of too complicated about this. Right? Okay, so let's write the algorithm. All right, so BFS. So notice that not only we give the graph as input, like in DFS, but there's an additional input, which is the starting vertex S. Okay, so BFS takes 2 inputs. So first we want to initialize the distance array. So we're going to say the distance of S is 0, and the distance of kind of everything except S, by this notation I mean like set all vertices that are not S to be this value. What should we set the distance to be? Yeah, either some special symbol, either null. What is often common when we talk about shortest paths, instead of using null, which is kind of not very suggestive, it is helpful to think about it as infinity, okay? Because sometimes you're going to be comparing distances, okay? And sort of thinking as something unexplored as of distance infinity is like a useful thing to do, okay? And then we kind of need to have a state of the algorithm. Now, in DFS, the state was given by a stack. okay, that kind of remembered what is there still to do, okay? This time, we don't want to use a stack because when we're exploring this one, let's say, and we are adding its neighbors on the things that we should do later on, we don't want to immediately explore this one, right? We want to first go around, right? And then go around the next bigger circle, right? So while a stack is a kind of first in, kind of last out, a data structure, we're going to use instead of a stack a queue, okay, which is first in, first out, okay? Because we want to add these things, and they should have lower priority than whatever all the other things are already in my queue, okay? So we're going to initialize a queue to be empty, to be just S, sorry, because we kind of, S is kind of, we know that it has distance 0, and that's our starting point. And so that's kind of initialization. The algorithm itself will say, well, while the queue is not empty, we're going to be doing things. We're going to ask the queue to give us the next vertex to work on. Okay? Maybe this vertex is in the same ring as the previous one, or maybe it went over, and it's the first vertex we're exploring into the next ring. Okay? And then we're going to say, okay, for every edge that comes out of view, if we have not seen it, namely if the distance of v is infinity, it is new to us, okay? Then we're going to inject that vertex into the queue. And then we're going to set the distance of v to be the distance of u plus 1. Right? This algorithm is precisely doing that thing over there. Do you agree? And maybe, let's see if I want to go through the example or not. Let me first talk about the running time. All right, so let's first talk about the running time, then we can see kind of the algorithm in action. So all this stuff is cheap, right? So we're just allocating an array of size v, n, right? So this is like linear in n. Here we just create an empty queue. Over here, again, we have all of these like recursive calls. Not quite recursive, but we have this queue that maintains the state of the algorithm, right? And we need to count how many operations we're doing, right? So how many times do we touch each vertex? Yeah, or we have like a constant number of operations per vertex, right? Because we may look at it, right? But then that's it. Like if it's new, then we do something interesting, like we put it on the queue. Otherwise, we put it back, right? For the edges, the same thing happens. Whenever we're looking at an endpoint of a vertex, okay, it is because it was on the queue. We put it on the queue because it had distance infinity. But when we put it on the queue, its distance changed from infinity to something finite, okay? So it is the first and only time that we put it on the queue. At some point, it will come out. So it means that we consider each edge, each directed edge, once. Okay? So the running time of this algorithm is n plus m, right? Like DFS. So this algorithm runs in order of n plus m. Again, it is similar type of global accounting where you look at how many operations you do per vertex, how many operations you do per edge, kind of add them up globally. Okay? Because kind of the algorithm doesn't really do things again with the same objects, and this just means that overall has a limited number of operations. Yeah.
Finally, a question
So the question was, can I explain, I guess, this line over here? So when we see that V has distance infinity, we know it's not on the Q. It's a new vertex. We've never met it. Okay? Visually, that's what's happening here. So I'm currently at U. U is on the Q, or at least was on the Q, because we ejected it, right? Now we're exploring all of the vertices, all the neighbors of U. Some of them, like A, already have distance less than infinity because we have processed them. Okay? They've actually already been on the Q. Others have distance that is still infinity because the first time we see them. So we set their distance to be the correct one, which is whatever is the distance of U plus 1, and we put them on the Q. What does it mean for them to put them on the Q? It's just for the algorithm to remember that whenever it's done with the circle and it starts with the next circle, it needs to know what to process. Okay? Those are the vertices that you put at the end of the queue, ready to explore when you're done with that circle. You have to be done with that circle first. Otherwise, when you get to the next circle, you don't know which vertices not to look at. Right? Good question. Okay. Right, so the running time is, again, linear, order of n plus m. Now, I'm not going to go through it in lecture, but if you really, really want to prove the correctness of this algorithm, actually is in a formal way, it's actually not that easy, okay? You need to kind of put down an invariant on the Q, and how the invariant on the Q relates to the distances from the vertices on the Q to A. And I think it's a good exercise to try to do it offline, okay? By trying to link this picture with the algorithm and see how if you can formally argue that the algorithm is correct. Okay, we've basically done it, but not to an extent that would really be counted as a proof. Okay, but we're not going to be doing proofs for every algorithm we talk about in class. Otherwise, we don't cover much material. Okay, so this solves the question of shortest paths on graphs where all edges are undirected and have the same weight. Okay? So the first relaxation that we're going to do is instead of looking already at directed graphs, instead we're going to keep looking at undirected graphs, and we'll give distinct weights to different edges. Okay? So now we look at a slightly more general problem. Let's see. I want to keep that stuff there. I'm going to get rid of this one. So let's call it shortest paths with distances. Okay? Or weights, sometimes they're called. Now, remember, whenever you're doing exercises or exams or midterms, most of the time, there is an answer using tools you already know. Okay? So you really need to become comfortable with trying to recycle and adapt ideas you already have. Okay? DFS took us very far. Okay? Okay, at some point, we started talking about shortest paths. It didn't help anymore. Now we talk about BFS instead. Okay? But we do have BFS that now works for this kind of problem. So our first question is, can we use BFS? Okay, or is there some way of using BFS to solve this more general problem? Okay, so the first idea would be to say, use BFS again. Now, this idea is kind of like ill-defined, right? what does it mean use BFS again? BFS specifically says, look, I am going unit by unit. Because I know all edges matter the same. So if I take 2 hops to go here, I know that it cannot be that there is another edge here that was much more heavy, and therefore it made sense to take this path. I would have taken this path instead, right? So somehow this envelope thing of BFS doesn't quite work. But there is something we could do instead by modifying the graph. Does anybody have an idea of how to modify the graph so we can run BFS on it? Yeah. Okay, so the idea is to take a heavy edge and split it down into a kind of sub-edges of unit 1 each. Okay? That's a good idea. So let's kind of think about it briefly. So kind of transform G into G prime such that kind of each edge, kind of, let's call it U, goes to V with weight with distance d, is replaced with an edge, kind of U, and then it will have kind of a temporary 1, temporary 2, and so on and so forth, up to V, so that here there are d unit 1 edges. So you're kind of, for the edges that are heavy, you slow down BFS on those, right? It will take him multiple and multiple iterations to get to this faraway vertex. Okay? Do we agree that this is a correct algorithm? Like this transformation will preserve the answer of BFS. Do we agree? Yeah. Okay. Is it a good algorithm? It's not a good algorithm, right? Can anybody explain why? Yeah.
There might be, like, extends the vertices, thus extends the time complexity. So the maximum complexity is the total of the length.
Okay, so there is this, yes, so the algorithm becomes slower because the graph becomes larger. I'm looking for an even sharper answer. Is this algorithm in polynomial time? Like clearly BFS was in polynomial time on its own. It was order of n plus m, right? The new running time, so let's write it here. So the runtime is, of course, order of n prime plus m prime, where n prime is the number of vertices in the new graph, and m prime is the number of vertices in the new graph, right? But really what we care about is how much are these as a function of n and m, right? That's really the measure against which we should compare, right? So maybe to make it, suppose we're looking at the graph that we looked at before, A, B, C, D. But now I add, the weights are, I don't know, 2 to the n, 2 to the n. This is not the same n. Let's say 2 to the a, 2 to the a, 2 to the 2a, and 2 to the 3a. Okay? What is the bit complexity of this graph? To write it down, how many bits do I need? Like, how large is this integer? How many bits? A, right? So you have a constant number of vertices, constant number of edges. So this entire thing has size kind of order of A, right? So that's kind of my input size is on the order of A. How many vertices V prime and edges E prime will I have through that transformation? Roughly 2 to the A, right? Yeah, I'm not keeping track of constants at this point, okay? Roughly 2 to the A, right? So now, on an input of size A bits, I'm running in time 2 to the A. That doesn't sound very good, right? So this is one way to sharpen the fact that, yes, the algorithm is too slow. In particular, it runs in exponential time. That's not a good running time, okay? But even though this is, to some extent, a terrible algorithm, it actually gets you kind of qualitatively a good chunk of the way to a much better algorithm. Okay, we'll discuss it next time. It's a famous and a beautiful algorithm called Dijkstra's algorithm. And it can be thought of, to some extent, as essentially whatever we're doing here, except that whenever you put yourself on one of these long edges, you move faster, okay? Because you anyways know that you're going to be walking, and you know there's going to be one, and one, and one again. The algorithm knows that, okay? So it's going to kind of speed up and make it all the way there. And we're going to write it in a way that instead of using a queue, it's going to be using a priority queue. And that would be the main idea of dealing with different distances, okay? All right, so that's what we're going to do next time, Dijkstra's algorithm.